Okay, so first I want to, well, I forgot to say an important thing in the last lecture, which I would like to correct now. So this is the formula we had for the impulse at leading order. And if you remember, I promised that I was going to keep the h bars with me everywhere. And then I never said why, which was a bit dumb. So I want to explain what the fate of the h bars, is in this formula. There's a h bar running around. I'm trying to do something classical. What gives, right? So now the h bar just appears in this formula as written. You can see it there, right? I mean, it's in this e to the I b dot q. So suppose I define q bar, which is q bar is q over h bar, right? So this q over h bar becomes q bar, right? And I can do that by wiping, right? So that is q bar. But then I should change the variables for all of these things too, right? So the question is, where does the h bars go? Well, I got 4 h bars upstairs here, minus 2, so that was 2 h bars upstairs, plus 1. So there's 3 h bars upstairs in this parameterization, h bar cubed, right? So that looks a little bit weird, but what about the amplitudes? Now here is an example 4-point amplitude in electrodynamics. Right? It's very similar in gravity. So where are the h bars in this formula? Well, there's a q squared there, so that q squared becomes q bar squared h bar squared. What about the any other h bars? Well, the p1s are just momenta, p1 dot p2, that's just momenta. That doesn't change its dimensions when I restore h bars. But the dimensionless quantity, when you have h bars in the problem, isn't e squared. It's e squared over 4 pi h bar c, fine structure constant. So if I want to make the e squared dimensionless, I've got to put another h bar downstairs here. And this just becomes h bar cubed downstairs. So that h bar cubed cancels that one, and they go away. Right? So that's what happens with the h bars. So it's the same in gravity, it's the same in any theory that makes sense classically. And just a quick remark about the homework. When I was chatting during the break, it became clear that I should emphasize that what I mean by solving the geodesic equation is work in perturbation theory at lowest order. So the 0th order thing is the particles are moving on a straight line. The lowest order thing is that there's a first order deflection. So if we put that in the geodesic equation, it becomes much easier. Okay. So on to new topics. All right. Look around with these blackboards. I'll start over here. Okay, so the second observable is going to be the waveform. Now, I'm still in a scattering situation. So that is going to be scattering all day because we're doing scattering amplitudes. So what that means is I'm going to take 2 massive particles. They're supposed to be, they're, essentially black holes because, what this scattering is building up is the metric of the Schwarzschild's metric plus interactions. So I shoot them at one another. They scatter. Something happens in the middle. My particles fly back out. And there's some gravitational waves that are emitted, right? So this, the waveform, h, as measured by some apparatus, some LIGO, it isn't going to look like the wiggly line that we get from LIGO. That happens because you've got bound states. This thing will look a little bit like a bang. Right? So well, that's the kind of waveform I'm going to be talking about. I'm going to use the same state as before. Let me see, I want to say anything first. Yeah, actually, let me say a little bit more about this waveform. So what is it that, that this h really is that the relativists measure? Right? The way I like to think about it is that it's essentially a measurement of curvature. So measurements, so people call the strain, talk about this h as a strain. The strain h of t is a curvature measurement. So that is to say that there is an equation that you can establish in a certain gauge. It's called the TT gauge, transverse traceless gauge. And in the transverse traceless gauge, this H now, Hij are two components of the metric perturbation. Right? So we're measuring these metric perturbations here. And this thing is given by the Riemann tensor at the position where you're making the measurement. So the second derivative of the metric is the Riemann tensor, and the H, the strain H, is a linear combination of the plus and the cross, these two different polarizations of the H, right? With some plus or minus I, which is conventional. Okay, so essentially what our friends at LIGO are measuring is the curvature of spacetime. Now, in quantum field theory, I'm not going to be able to give an expression for the curvature, but what I can compute is the expectation value of the curvature. Right? So we will have a curvature operator in perturbative quantum gravity and take its expectation. Okay. Yeah, this one looks dry. Good. Okay, so we'll pick the same state. So remember, there's this three-step recipe. So step one was to pick an observable. Well, I'm going to talk about the H. Step two is to pick the state. So the state is going to be the same thing, psi, integral d phi, p1, p2, phi of p1, p2. I'll translate one particle with respect to the other. And now I'm just setting h bar equal to 1 because I finally remembered to talk about the h bars. Okay, now in the far future, the state will be, so this is the same state, but this is initial. Well, the final state is S psi. So the expectation value of the curvature in the future is going to be the future curvature is S dagger Riemann tensor operator S psi. So that's the thing I want to talk about computing. Okay, well, okay, yeah. So now
where did the H bar go?
Hmm?
Where did the H bar?
Oh,
go?
I set h bar to 1, right? Yeah. Well, now I'm now I'm now I've talked about h bar.
Okay.
H bar is here. H bar went away. H bar is always going to go away.
Yeah.
This is filled with confidence. Yeah. There is a story, a very similar story about the H. So if you wanted me to do it, it would be painful, but I could track the H bars here and show they cancel at the end. It's a little bit more of a story when you have this thing in here, because there are various weird fractional powers of H bar. It's like 7/2 or something weird. And when you keep them all there and you compute your amplitude, you find that they all cancel off and you're happy. Yeah, so, sorry, I'm not going to track them in this lecture. Okay. Well, another painful thing is that we need to remember what the Riemann curvature operator is, and I need to expand it, right? I mean, I'm in a world where the curvature, or where the metric is eta mu nu, flat space, plus a h mu nu, or an expectation of h mu nu, right? So I'm going to expand this Riemann curvature in powers of perturbations, right? I mean, there's going to be, so we need to remember what the Riemann tensor operator is expanded out perturbatively. And at first that might seem very painful, but there's a very nice simplification. So this is actually not too bad. Now, I write g mu nu as an operator as eta mu nu plus kappa h mu nu, right? So I'm going to have that perturbative coupling kappa that was around yesterday. I insert it in front of the metric so that the h as a field is canonically normalized. So that means there's going to be a kappa here. There's a sign convention, which I'm going to pick. I'm going to pick out a minus sign there. There's a factor 2 because Riemann tensors are computed out of Christoffel symbols, and Christoffel symbols have a half in them. And otherwise, there's a psi, there's an S dagger. Now, Riemann tensor has two derivatives, and at linear order, there's going to be just one H. And so I've got two derivatives, one H, and then I just have to remember the symmetries of these indices. So let's see, so I'll have d mu, d rho, quantum field, H rho nu sigma, and then plus or minus permutations. So it'll be some term. So the plus minus index permutations here just mean you should swap mu and u and rho and sigma so that the Riemann tensor has the symmetries it's supposed to have, right? So antisymmetric under mu goes to nu, rho goes to sigma, and totally symmetric under a pair, change the two. Okay, so that's some set of terms. And then there are higher order terms, psi, s, dagger. There's terms that involve h squared and h cubed, etc. Okay, so at first that seems very formidable. We have an infinite series here, but there is a very useful simplification. So now I'll soon show you. You'll soon see that the expectation value of h goes like 1 over distance. So the expectation value of h squared is the square of the expectation value of h classically. Right. So this term here, which has 2 powers of h, has a 1 over distance squared, right? I'm interested in situations similar to what LIGO is measuring, where the black hole scattering or the black hole phenomena, the event, is many, many, many light years away. Right? These are astrophysical distances. So when you have an astrophysical distance, 1 over r squared is 0. Right? 1 over r is already like, you measure it by looking at displacements of order the size of a proton. 1 over r squared is 0. Right? To any useful physical situation. So that is just 0. And this is even more 0. I've got lots of more zeros. Right? So we get to restrict to the leading order in h. Right? That is just because of the distance fall off. This isn't to say that I'm doing linear, that the whole thing is linearized. I mean, I've linearized this Riemann tensor. So still, so the expectation value of h is nonlinear. So there will be a nonlinear, there'll be 1 power of 1 over r, but many different powers of kappa inside the Riemann tensor. Right? So this is exactly what happens in LIGO. So the LIGO signal is really just the 1 over distance part, yet it's a very nonlinear thing, right? So the nonlinearities of general relativity are there, but we get to throw away some terms we don't want because of the distance scaling. Okay, so that's a major simplification. I'm really computing the expectation value of the linearized Riemann tensor, but the h inside there will be a nonlinear thing. Okay, good. So now to continue expanding this operator, I'm going to write out what h mu nu is as a quantum field. So I'll expand this h mu nu in creation and annihilation operators. So in an equation, I'm going to write h mu nu of x as an integral. So again, quantum fields are integrals over on-shell phase space. I get another one of these d-phi integrals. There's a sum on helicities. I'll call that a sum over h. And there's a polarization tensor for helicity h, an annihilation operator for helicity h, e to the minus I k dot x plus Hermitian conjugate. And recall that the polarization tensor can be rewritten as a product of polarization vectors. That makes the writing a bit easier. Good. So I shoved this in here. And maybe I will go over to this side of the board. No, sorry, let's do it this way. It's more canonical. Okay, thus. So psi S dagger Riemann tensor x s psi equals. Very good. So we'll have the kappa over 2. This integral d phi of k, so I'll take that out. Now, these derivatives that are sitting out here come inside the quantum field and they bring down 2 powers of minus ik, right? So the 2 minus i's give me a minus sign, which will cancel that minus sign, which I cunningly put here. So that's gone. And otherwise, these derivatives just bring down k's, right? So I get a k mu and a k rho, right? And I'll also have some e's, which I write in terms of these epsilons. So it is easy to see that you will get anti-symmetrized k mu, epsilon u, k rho, epsilon sigma. E to the minus I k dot x times a bracket, which is psi s dagger ah of k s psi, and then another term, which is just the complex conjugate of the one I've written. So this is the expectation value. Now, this thing here is very much along the lines of what Simon was talking about a few hours ago, right? S dagger AHKS, right? That's one of these B's, an annihilation operator in the future, right? That's what this S matrix is doing. It's moving that annihilation operator into the future. So I can write this thing as psi, just using Simon's notation, and BH of K psi, right? So annihilation operator for a graviton in the future with momentum K and helicity H. Okay, so in here we're seeing the links with Simon's lectures. Awesome. Okay, another thing that's sort of obvious about this formula is at the level of the quantum field theory, this is just the thing you need to compute, right? There's got to be, there's some integrals, there's some other stuff to do, but all of our Feynman diagrams and loops, etc., they're all going to involve this quantity here. So I give this a name. So I'm going to define alpha h of k to be this thing here, psi bh of k psi. So we gave this a funny name. This is just the wave shape. Yeah, it's just, it's a wave shape because it's the thing, if you've got it, then you know the shape of the waves. It's a very sophisticated nomenclature, Okay, so now I'll talk about this wave shape in some detail, but first of all, let me mess with the forwards. Okay, so first there's an interesting thing to do first. So I want to come back to this business of the 1 over r. Yeah, the 1 over distance, sorry. So there's a slightly unfortunate thing that many of my students might be aware of, but in my way of speaking English, the letter that comes after P and Q in the alphabet is pronounced or. And that makes people confused sometimes. Well, if you hear me saying or in an unexpected way, it probably means ah, I'm sorry, but that's just the accent I grew up with. All right, so I'm going to do this integral over the phase space of the photon, or the graviton, this K integral here, and you'll see that I'll get this 1 over r factor. Well, I'll tell you, I get the 1 over r factor. It's a very interesting integral, so worth spending a few moments on. Okay, so this wave or this observable here has the structure. Well, this has this sort of structure. Well, the observable involves integral d phi of k. And then there's some stuff, with indices. So let me just call it ji of k. I'm not really going to care about it too much. I'm going to essentially do a stationary phase type calculation. I'm really caring about the stuff in the numerator. in the exponent. So there's an e to the minus I k dot x plus complex conjugate. Right. Now this complex conjugate is just going to go along for the ride. Goes along for the ride, so I'm going to dump it. So everything I say about the explicit term is goes along with the complex conjugate with this term. Goes along for the ride. Gosh, 4. Okay, so I'm just going to study this integral for a moment, right? That's right. So if I break this integral up, there's an integral over 4 components there, k0, and then 3 values of the momenta, k vector. Right? If I integrate over the k0 using the delta function, I'll get 1 over 2 k vector. So I'm going to write that as an integral d omega over 2 omega. So integral d2 phase space. So this omega is the modulus, the magnitude of the k vector. Right? I've done the k0 integral. It gave me that 2 omega downstairs. This is the k vector integral. And then these are the angles associated with the vector k. So now this thing involves ji of omega times omega n hat. Let's say n hat are the angles associated with this solid angle. And e to the minus I omega t, and e to the plus I, well, it's k vector dot x vector. So k vector involves omega n hat, a distance. That's right, it's omega r, n hat dot r hat. Okay, so this is the sort of integral I need to do. Now, when this distance r is very large, you can simplify this integral. And there's various different approaches to simplifying that integral. Maybe the simplest one to think about is a stationary phase, right? So the r is very big, that phase is oscillating very rapidly, and because of that, you can perform the integral in a saddle point approximation. The result is, so I'm just going to tell you what the result is. Yeah, well, it would have been good to pull out some of these factors of 2 pi. So that was a factor, there's really a factor of 4 pi squared downstairs there. That came out of these d3k's, whatever, there's from 4 pi squared. You'll get a 2 pi from doing this integral. So there's going to be a 1 over 4 pi. You'll still have this integral here, which I can now think of as a frequency integral. And from the stationary phase, you pull down a factor 1 over I omega r. The omega cancels. You see it, gosh, there really is an omega upstairs here. Sorry, so there was an omega downstairs, but when you think of this, there's an energy downstairs from doing the k0 integral. Right? However, then when I'm thinking of this as an integral over 3-dimensional spherical coordinates, there's an omega squared upstairs. So you really get an omega upstairs. But now from the stationary phase, that actually gets cancelled off. You just get this distance factor here, the I. And you end up evaluating this thing as omega r hat. And all that's left here is e to the minus I omega t minus r. That's so. Let me see. So it's important that that is an r hat. So now what's happened here? Well, you pick up that 1 over distance, right? And that's the justification for this statement here. So the Riemann tensor falls off like 1 over distance. Its time integrals fall off like 1 over distance. And therefore, the higher powers of the metric fall off like 1 over r squared or r cubed, right? According to the power. So for this justifies leaving these things out. But a cool thing has happened here, right? Because after doing that stationary phase, you find that the polarization vector, this was the momentum of your graviton, which was previously just something that you're integrating over, becomes a frequency, in one component, and the other components are the distance or the unit vector from the event to the person, to the LIGO, right? So now the gravitons are actually traveling at the detector. That's a non-trivial thing, how this emerges from this form, I mean, you might think, oh, of course, the momenta, sure, the momenta are coming at me, but you've got an integral over all the momenta. The fact that they end up coming at you, that's non-trivial. It's interesting. Anyway, so that's how this happens. It's a stationary phase. Okay, so now let's go back to our wave shape. Okay, yeah, sorry. I wanted to say one or two other words about this. So just on this, yeah, since I just sketched that integral, I have written many pages about this integral. So let me give you two references where you can look this up if you're interested. So one of them is this review I mentioned before, but I expanded even more pages on the same integral in this paper. Yeah, anyway, yeah, anyway, yeah, it's a very interesting thing. Okay, and the other comment here is, well, there's really two solutions to the stationary phase conditions, and I've kept here the one that is retarded. So the one that has, there's also an advanced term which has T plus R. So T minus R is the thing that's constant on gravitons coming from the far past towards the detector. And the T plus R are the ones going out in the other direction. Okay, excellent. So let's then go back to this wave shape and express it in terms of amplitudes. Or, well, maybe I should say amplitudes. Oh, they're amplitudes. Okay, so in other words, I'm coming back to this quantity here, this alpha. Yeah, so I define this alpha in terms of an annihilation operator in the future. But I can now expand these states of psi in the same way as I expanded the states in the context of the impulse. So I have some phase space integrals for the momenta in these psi's. There are some wave packets. There's this exponential stuff, e dot p1 prime minus p1 minus p1 prime. And now what's left is the scalars, bh of k, p1, p2. And this really, this thing here really is what Simon was talking about, right? So, so this p1 prime, is the way Simon was writing them, was like this. So it is, so there's a zero. I'm creating particles here in the adjoint, but they're in the past. So these are A of P1 prime, A of P2 prime. Here, there's this annihilation operator. It's now in the future. And here, there are creation operators in the past. These A's, like, so one thing about them, that there are all creation and annihilation operators in the past, but they're also for these scalar fields of 1 and 2, type 1 and 2. The B, it's got a H, right, because it's an annihilation operator of a graviton. Okay, and that one's in the future. Right, so this is exactly the kind of quantity Simon was talking. Now, well, it's useful to give this thing a name. So it's not an amplitude. It's an in expectation. So I'm just going to call it an expectation. Maybe I won't call it an expectation very much, but I will also give it a notation. So I will set IE, well, it's a script E because amplitudes are script A's, times delta 4 P1 plus P2 minus P1 prime minus P2 prime minus K. So I will define this thing to be this matrix element. I can write it this way, it's a little shorter. Okay, and it's interesting and fun to expand this out and look at what it is in terms of familiar amplitudes and how, how it actually differs. So let's, start. Obviously, the first thing to do is to try and understand this thing at tree level. So at tree level, right? And at tree level, well, way to go ahead and just start understanding this thing is to remember, this B, it's just S dagger A S, and S is 1 plus IT. So at tree level, let's say E0, so tree approximation, delta 4, I won't write its arguments, is P1 prime, P2 prime, 1 minus IT dagger. That's S dagger, A, H of K, 1 plus IT, P1, P2. Okay. Now, this annihilation operator, if it hits that 1 on these states, it will annihilate the state, right? This state has no gravitons to annihilate in it, right? So if the annihilation operator just hits it, you get 0. So I can drop the 1. Right? So you just need to keep the t. You need to keep that transition matrix. At tree level, then I can ignore this t dagger, right? The t's are going to carry more perturbative couplings, right? The tree level tree level contribution is the one with the least couplings. So I will minimize the number of powers of kappa in my problem if I just ignore that. So that's just the tree. I'll talk about the loop in a moment. So for now, I'm just going to leave that aside. Right? Excellent. So in other words, the lowest order approximation is P1 prime, P2 prime. Now this annihilation operator can act directly on the bra part of the bracket. So the annihilation operator acts directly on that, and it creates a graviton. Well, there's a graviton K and helicity H. There's an I and a T matrix. Right. So it's just directly equal to the amplitude. No difference. So this is equal to I amplitude. Let's say, well, it's a 5-point tree level amplitude times the same momentum conservation. So in other words, this E object is just directly equal to the amplitude at tree level. Okay, so that was easy. Excellent. I can drop the T. So the question was, why can we say again why I can drop the T dagger here? And I'm just dropping it because I want to work at lowest order in perturbation theory. All factors of T and T dagger carry some perturbative couplings. They're amplitudes. So if I just leave that out, then I'm minimizing the number of powers of coupling I can get, at least from the left-hand side. I have to have this T on the right-hand side here. It has to be there or else it gets 0. So what I want to do to get the lowest order approximation is take the lowest order approximation to just that T. And that's why I get a tree level 5-point amplitude. Yeah. Is that clear? Okay, overwhelming enthusiasm for clarity. Good. Take that as.
Wrong about keeping the term T dagger here again.
Well, if you keep the identity here, so I guess the question is why can't I keep this T dagger in that one? That's your, yeah. So this one, you see, this annihilation operator, if there's just that one there, if there's no T, this, just kills that state. So I leave that out. Yeah.
Sorry, one more, but you're dropping one of the priority queues and the next two as well. You keep the real tree level amplitude.
Yeah, that's right. So in this T, I'm just extracting the tree level bit and throwing away every other higher order bit. All the other higher order bits would start talking to these T daggers.
Exactly.
Yeah. Excellent. Yeah, good.
Can you please briefly go over where you get the helicity index from that approximation?
Now, let's see. So this helicity and the H index there. Yeah. So, well, it started life, this blackboard. Well, I mean, it started, let's see, where did it start life? Maybe I need to wield the stick. So it's really the helicity index there on the annihilation operator that's just part of the definition of the quantum field. Right? So the quantum field always involves the sum over helicities when you've got a bunch of particles of different helicity. So that's why there's a helicity index on this A, and it's just been tracking through the problem. So that helicity, this H, is just the same as that one. No. There's so this is really yeah. So this expectation depends on the helicity of the graviton that's coming off. In the total, now let's see. So I think maybe is it here?
What about the polarization? That's my
Yeah,
second
exactly.
question.
So there's helicity indices on these polarization objects, which are being contracted against the helicity index of that. So yeah, so arguably I should have H indices there. I really should have a sum over H, so that's definitely, yeah. You should be a sum over H here. And you could put an index H there if you want. Is that something to, yeah. Yeah, okay, yeah, yes. Yeah, I think that's the only place where I omitted the sum merchant. Okay, good. Now, where am I? So yeah, let's. Okay. So plan now is, well, I will insert this expression here for this expectation into the wave shape. So I'll just simplify that again so you see what actually needs to be computed to extract a waveform at leading order out of this. So it's pretty straightforward. So the wave shape, this alpha thing. Now I'm going to perform similar manipulations to the ones in the impulse, but I'll do them a bit quicker. So I'm going to take particle 1, particle 2, P1 prime will be P1 plus Q1. And P2 prime will be P2 plus Q2. And then my gravitons will come out with momentum H. So the wave shape here at lowest order now is going to involve just the 5.3 amplitude. And I'd like to simplify all this phase-space stuff and you know, this crud involving you know, wave packets, which you know, classical physics shouldn't be able to see. So it's very simple to do this. So you know, the mechanics are exactly the same as in the impulse. There's only one slight difference. In the impulse, this was a Q and that was a minus Q. Now there's a Q1 and Q2 that add up to K. But otherwise, everything goes through just the same. So I will eliminate or I will change variables in the P1 prime integral to an integral over Q1, change variables in the P2 prime to an integral over the Q2. These wave packets will then involve shifts. The shifts will have, you know, be order Q, and I will neglect those shifts in the wave packets. So I'll get an integral over phase space involving 5 P1 P2 squared. So, and I will just shove that into a big bracket. The big bracket will have the same meaning as before. So I will be left then with an integral over the Q1, an integral over the Q2. Delta functions, on-shell delta functions, which involve 2p1.q1 plus q1 squared. But as before, I will neglect the q1 squares carefully. So it'll be those two delta functions. There are theta functions, which I'm just setting to be 1 because the q's are very small to the compared to the p's. And there's an e to the I b dot p1 minus p1 prime. P1, well, that's going to be minus e to the minus I b dot q1. And then there is this matrix element here. That involves just a 5.3 amplitude and a factor of I. So times I a 5, 0. And there's still now there's a conservation of momentum, which is expressed in this. I could have done this Q2 integral against that delta function if I wanted, but you know, it's more symmetric to keep it here. So that is, so that's a pretty explicit formula. You just got to go ahead and compute the 5.3 amplitude and do some integrals. Yeah. You take this alpha h of k, and well, you can put it into this formula here. You know, so this is this alpha h of k. So put it into that formula here, but the phi integral has been reduced to a one-dimensional frequency integral.
Sorry,
Yep.
Donald, could you repeat quickly what the double brackets are?
So the double brackets, their job is just to say you should do your calculation here, and at the end set these p's to be the classical value of the momentum, and really only apply these delta functions as written right at the end. Again, that's this sort of caveat, which I'll talk a bit more about tomorrow. For now, it's just really just set the momentum.
Thanks.
Yeah, so just a word about the frequency integral. You know, a lot of gravitational wave analysis is actually done in frequency space. So you don't do the frequency integral, well, nobody cares. Actually, in some cases, it seems to make life better to do the frequency integral. Sometimes, you know, you do integral, you get nicer results. This thing comes out in terms of modified Bessel functions. If you just do these Q integrals, if you do the frequency integral, you get square roots of functions of time. And the result, this initial result, you know, the result of doing these integrals with the tree-level 5-point gravitational amplitude was originally found by Kovács and Thorne using pure gravity in 1978. So it was physics from the last millennium, which you're catching up with. But that was the state of the art in relativistic waveforms until the last year or two.
Donal?
Yeah.
You're going to have a plus CC in the final formula, right?
I was just about to write it. Thanks, Rishabh. Yeah, it's not even in my notes. And one last comment about this. So this amplitude here, so I mean, I really mean the amplitude in gravity. So that is an amplitude that you can construct using the BCJ double copy. It's actually an interesting calculation. It is very straightforward to find numerators that satisfy color kinematics duality, as I mentioned in the last lecture. The only thing you need to be careful about is the sum over states, because you do want the physical states that involve gravitons, not involving these dilitons and axions. So there's some job to weed those out. Okay, so that's the tree level story. So the last thing I want to tell you about today is just what the one loop, what this one loop E object looks like, this expectation. So that will connect a little bit more with Simon's lecture from earlier. Okay. Let me see. So, well, let's go with this expectation of one loop. Okay, so I'm interested in this object here, this matrix element of the B. But now I'm going to work it out at one loop. So I'm going to return to this expression here, but now I don't get to throw away the T dagger. So now Simon worked out, explained what this thing looks like in terms of Feynman diagrams using his advanced blobology. Another example of fantastic terminology. I'm not as good at blobs, so but I'm good at commutators, so I'm going to expand it out with commutators, and we'll get the same sort of result. So it's convenient, at least convenient to me, to reorganize the E using unitarity, which is a continuing theme in all of these lectures. Right? So unitarity is the statement that S dagger S is 1. In other words, 1 minus IT dagger. 1 plus IT is 1. And that tells me that T minus T dagger equals IT dagger T. Okay, so I'm going to use this to simplify the structure of this object at one loop. Now, the thing I have to worry about is, so there's a P1 prime, P2 prime here on the left, and I'm just going to let that come along with the right. I won't write it. Oh, but I will need to keep everything else here. Yeah. So I have AH of K. Actually, let me leave out the K. I'll just write AH for now. That comes with an IT. And then there's a minus I T dagger AH T, all of this acting on P1, P2. There, I'm feeling a little uncomfortable. Just check my notes. Yeah, so there's an I. Oh, yeah, I'm stupid. So there's no I here. And there's a plus. Yeah, and there's a minus. Ah, I see. I pulled out the I here. That's minus I. Let me see if I can. Yeah, okay, so I'm just leaving out the I as well. So I have AH on T, and then a minus I T dagger AH on T, right? Because I'm pulling out the I. Okay, so now what I'm going to do is write this T here. Well, maybe I can do it here. So I'm going to write this thing as AH on a half T plus T dagger plus a half T minus T dagger minus I T dagger AH T. That closes that bracket on P1, P2. Okay. So, and this is handy now because by writing this half T minus T dagger, I get to write it in terms of, I get to use unitarity. So I'll just continue over here. So there's an AH multiplying, well, I'll write a half T plus T dagger as the real part of the T matrix. So that is the real part of T. So that's the first term. A half T minus T dagger, I will use this unitarity to write this as plus I over 2 AH. I'm leaving a little bit of space here for myself. T dagger T minus I T dagger AH T, and all of that acting on P1, P2. Okay, now it's possible to simplify this a little bit further by introducing commutators. Now, if I just put a commutator here, well then in one term, the first term, the AH is where it was when it started. And in the other term, the AH is on the other side where it annihilates the state, right? So I didn't do anything. Similarly here, I can put a commutator there, right? So now, you know, the other side, I didn't do anything. But what's nice is you can see that these two terms start talking to one another, right? So there's going to be one term, and if I expand out this commutator, there'll be a term where the T dagger is outside there, and it's exactly of the shape of this term, it just has a different coefficient. So this thing is equal to AH, real part of T, plus I over 2, so there's one term, AH T dagger, T minus I over 2, T dagger, AH T, acting on my state. Okay, so yeah, so that's all that happens. Now, it's interesting to note that you know, so this term here, this term here, you know, the minus sign here, this is this cut term, this K-mod cut term, well, this term. So that means that sign is coming from the cut, and its job in life is to flip the sign here. And yeah, let me see, am I saying that right? Yep, okay. So it's just flipping the sign here relative to what it would be for the amplitude. So the amplitude was just, and that's all, it's just it flips one sign. Okay, so now let's draw the actual Feynman diagrams, or the cut diagrams that you get from these two terms here. This real T, you know, is in a sense the real part of the amplitude, right? Matrix element of the real part of T. So these are the terms that are interesting in terms of, you know, they involve these cuts. Now, the way I like to think about this is, so I think of the T matrix. So I like to think of the T matrix as, some coefficient function, which maybe is a distribution or delta functions involving momentum conservation, and then a bunch of creation and annihilation operators. Right? So I think of the T matrix as being some coefficient functions, with maybe some gravitons, K1, K2, and some massive particles with P1, P2, P1 prime, P2 prime. There could be a bunch of things like this. This is just one term in the T matrix, and then we'll have, let's say, an annihilation operator. Let's say I create some graviton. This K1 could be an outgoing, annihilated graviton. These would have some helicity indices, H1, H2. They'd be summed in principle. There's an integral over phase space and a sum over helicity. Phi, helicities. Oh, great. These are gravitons. Annihilation operators for scalar particles, creation operators for outgoing scalar particles, etc. So these are the kind of, that's the structure of the S matrix in my head. So just a bunch of creation and annihilation operators. Creates and annihilates particles. That's what amplitudes are. So terms like this, where you have a commutator, you're going to get nothing unless there is at least one creation operator for a graviton in the particular term for the T matrix you're picking out. So similarly here. Now, at one loop, there's a further simplification, which is that I can ignore the conjugate. That wouldn't work at higher loops, but because of unitarity, one loop. Well, you see what I have two T's here already, so I'm working at a one loop order. The T dagger is the tree level T dagger, so I just got to throw away the conjugate. So that's just because I have two of them. Okay, so very good. So now, so it's interesting then just to write out what these two terms look like. So bear in mind that this term here, which has this funny minus sign, involves incoming momenta P1 and P2, these guys. It has to have a graviton in it, at least one graviton, because there's an annihilation operator there. There has to be something for it to commute with. And now my particles 1 and 2 are stable, so they have to come out. And then one loop, well, one loop means that you have 5 powers of coupling. So all I can do is put a 4.3 in there. So this term here is coming from this. It's the only term you can get out of this. So that's got a funny sign. But there's also other terms, cut terms. So this term here, for example, well, one way you can think about this term, one part of it involves a picture, a structure very much like this. So you get out of this T, a 4-point amplitude, certainly nothing to stop you doing this. This one here has to have a one graviton associated with it, so I will get a diagram like that. So these two diagrams are two diagrams that certainly pop out. But this term actually has more possibilities. So there's another possibility from this guy, which is that I have to connect this T to my two incoming particles. But there's nothing to stop this T from having radiation. I mean, it could just be a 5.3. There's no reason why it wouldn't be. So I can have a 5.3 coming out. Now, this annihilation operator commuting with the T, it has to have a graviton creation operator. And there is a way I can make that work with 4 powers of coupling. It's this way. So this guy just comes straight through. And the other guys, So well, this is sort of the interesting term. And there'll be a term which flips this. So just, the blob on the other line. And that's it. There are all the possible cuts. Now, these ones here are pretty interesting because they're associated with the physics of radiation reaction. And you can more or less see that in the picture. I mean, in the first blob, you radiated a graviton. In the second one, the particle reacts against the graviton it radiated. So this is a radiation reaction contribution. These two terms here are kind of very similar. They look visually very similar. And the cut just flipped the sign of that term there. So what it does is it sort of raises the possibility that these two things could cancel. And they do in part. And that cancellation is relevant. It actually, you know, well, I talked about the powers of h bar in tree amplitudes. One loop, you'll find that there's one too many powers of h bar downstairs, which is a bit of a bummer. But what happens with these powers of h bar, excessive powers of h bar, is that they cancel in these two terms. This is the only place they are. And they cancel because of that minus sign. If this was a plus sign, there would be one too many powers of h bar downstairs, and the whole thing wouldn't have a classical meaning. Right? It's crucial that there's a minus sign there. It's the only way this thing can make sense. Of course, the reason why this is happening is that this, one point of view is that these pluses and minus signs are arising because of the I epsilons in the propagator denominator. So this is arising because this is a retarded, an in computation. But it's also the observable that has classical meaning, which is why the h bars are working. Okay, yeah, question. Is it obvious why I should get two contributions? Which two contributions, I guess?
The ones that you said. Sorry, I'll repeat.
Yeah, these two?
I was asking, yeah,
Or-
why is it obvious that the one with the minus sign, the one with the plus sign cancel?
No, actually, yeah. I mean, the thing, if you write down the expressions, they do look a little bit different. But there are some, so if you expand on the powers of these q, say, oh, this q is small compared to those p's, then you'll immediately see that they start to cancel.
Oh, it's a feature of the approximation.
It's
that
a
we're
feature of the
making.
classical approximation. That's
Oh,
right.
okay, okay. Because otherwise, could there be like some kind of causality effects because of
Yeah,
the one
I
coming
guess
from
that's right. I mean, certainly it's true that these things are all adding up just so you get the correct causal propagators.
Okay, okay. Thanks.
Yeah, well, that's all I have to say. So I just answering
And
questions.
one more question about
Yeah.
these terms. These are, so at finite but small h bar, is there physical interpretation for these diagrams individually before they cancel?
Yeah. Yeah, none that I'm aware of. I mean, they do, I mean, there are terms which survive. I mean, the cancellation is not complete even in the classical limit. So they do contribute terms that survive, and yeah, which I guess are related to, well, there's interesting phenomena actually. So there's a connection to IR divergences. So this object is, this waveform is IR divergent also in classical physics. And there's a connection between these and these particular diagrams and IR divergences. So there's something about long time propagation. Otherwise, they sort of contribute, terms that you get from geodesic or sort of Lorentz force type interactions. Yeah.
I was just wondering if you could kind of generally comment, presumably at higher loop order, you need to start putting in loop level GR amplitudes. And could you just comment, like, how hard is it to deal with the axion and the dilaton in those situations? How high can we go in those? Are they evaluated in some classical approximation?
Yeah, so constructing these amplitudes is indeed a bit of a job, particularly at loop orders. So there are, well, various different approaches actually. So one approach I should mention, I've been meaning to mention, is to use heavy mass effective theory, this Heft stuff. So that's one way of constructing the trees. And those trees have nice properties. They have nice color kinematics properties, and you can start sewing those together to get so you have Heft amplitudes on some sides, and you sew them together to get the actual loop amplitudes. That's one kind of approach.
But you have to continuously be projecting off these additional degrees?
Well, because Heft has nice trees, so then when you sum, you just sum with projectors.
Okay.
So, and you might do some work to make the sum, the amplitudes very nice, so that the sum over projectors is simple, because the sum over projectors becomes a bottleneck itself as you go far enough. Other ways of doing it are just to construct them with generalized unitarity. So cut, some maybe clever tricks, or some tricks you can use to keep these trees a little bit under control, and then again sew with projectors.
Okay, thank you.
Yeah.
Hi, sorry. Maybe I missed it, but you wrote diagrams for the commutator terms, but Did you say anything about this first term, like,
No, yeah. So this first term, in a sense, just goes along for the ride. It's actually very interesting in its own right. It's less related to what Simon was talking about, but yeah, I mean, one way to, there's a whole story about how one could go ahead and compute this real part. So in this context, actually, it's a little bit interesting that if you want to compute that real part, you find that you have to cut one massive line, just one. So diagrams like this. Let me see, do I have a place to write a diagram? Yeah. So you have diagrams like this. So you just cut that one massive line there. And that's a way to actually construct these real parts. Everything else, every other propagator you write as what they call a principal value propagator. So it's summed over the I epsilon prescriptions. Again, that's something that people meet in classical relativity, classical general relativity, the classical approach, these PV type propagators. So here they just fall out when you split things up into this real part on the cuts.
Any last questions? Well, if not, let's thank Donal